The Living System, Episode 3, Growth as a Decision System. At first glance, plant growth appears continuous and automatic. A stem extends upward, leaves unfold, roots expand outward into the soil, and from the outside it can look like a simple process of accumulation. More light leads to more leaves, more nutrients lead to more growth, and more time leads to more size. But this interpretation misses something essential about what is actually happening inside the plant at every moment. Growth is not a straight line. It's not a constant expansion. It's a sequence of decisions made continuously across the entire organism, where every new structure is the result of internal prioritization under constraint. A plant does not grow everything at once because it can't. Energy is limited, nutrients are confined, and environmental conditions are constantly shifting. Because of this, every part of the plant exists in a quiet form of competition with every other part. Roots compete with leaves, leaves compete with stems, structural expansion competes with metabolic maintenance. Even within a single region, different growth points compete for resources, signals, and chemical availability. What emerges from this is not uniform growth, but regulated allocation. At the center of this system is the idea that a plant must constantly decide where energy and resources go next. These decisions are not made in a centralized location. There is no single control point issuing instructions. Instead, the plant relies on a distributed network of chemical signals that shift based on internal demand and external conditions. Hormones, nutrient gradients, water movement, electrical potentials, and light exposure all contribute to a constantly updating internal map of priorities. This map determines which tissues expand, which slow down, and which remain dormant until conditions change. One of the most important distinctions in this system is the difference between growth sources and growth sinks. Certain parts of the plant act as energy producers, while others act as energy consumers. Leaves function primarily as sources, converting light into sugars. Developing roots, stems, and reproductive structures function as sinks, drawing on those sugars to support construction and maintenance. But this relationship is not fixed. It changes continuously as the plant develops and as environmental conditions shift. A young plant may prioritize root expansion to establish stability. Later, canopy expansion becomes dominant, and eventually, reproductive structures take priority. At each stage, the internal hierarchy of energy distribution is completely reorganized. But this system of allocation is only one part of the decision-making process. Beneath it exists a deeper layer that determines whether nutrients can even be used in the first place. Because energy alone does not build structure, and nutrients alone do not guarantee growth. Everything depends on whether chemical conditions inside the plant remain within functional limits that allow biological reactions to occur correctly. This is where ionic balance becomes critical. Nutrients in the plant are not stored as raw elements in isolation. They exist in ionic forms, primarily as positively charged cations and negatively charged anions. These charged particles are not just passive materials. They are active participants in biochemical reactions, binding to proteins, enzymes, and cellular structures that determine whether metabolic processes can proceed. When this ionic environment is balanced, proteins fold correctly, enzymes function efficiently, and nutrient uptake remains stable. But when the balance shifts too far in either direction, the entire system begins to lose efficiency at the molecular level. This is not a visible failure at first. It is a biochemical disruption that affects how nutrients are absorbed, transported, and utilized inside the plant. And this is where pH becomes one of the most misunderstood control points in plant biology. Because pH is not simply a number on a fucking digital meter. It is a measure of hydrogen ion concentration, and it directly influences the availability and behavior of nutrients in solution. It determines how strongly elements bind to one another, how easily they separate, and whether they remain in a form that plants can actually use. If the pH shifts too far in either direction, nutrients may still be present in the system, but they become chemically inaccessible. This is often misinterpreted as deficiency, when in reality, it's a failure of chemical availability rather than absence. This is also where measurement becomes complicated, way more complicated than most people realize. Many of you assume that these digital pH meters provide absolute accuracy, but in reality, their readings are out to fucking lunch and highly dependent on calibration quality, electrode conditions, water sources, and ionic interferences. In most cases, especially with highly purified water, such as reverse osmosis or with mineral-heavy source water, readings drift significantly without obvious indications. It is not uncommon for digital readings to diverge from actual chemical conditions in ways that are large enough to affect interpretation of plant health. In these cases, simpler chemical indicators such as litmus-based systems or reagent drops can provide a more chemically consistent reference point because they respond directly to the hydrogen ion activity rather than relying on electrical interpretations that the meter cannot accurately read. This really fucking matters because the plant does not respond to the number on that fucking meter. It responds to the actual chemical environment around its roots and within its tissues. Sorry, I'm getting a little worked up on this one. I've been trying to tell people this for years, but people refuse to check their meters. So, when pH is outside optimal range, the effects are not limited to nutrient availability. Ionic imbalance begins to interfere with protein structure and function. Proteins are not rigid objects. They are folded molecular structures held together by weak chemical interactions that depend on stable ionic conditions. When those conditions shift too far, protein folding becomes distorted. Enzymes lose efficiency. Transport proteins fail to bind correctly. Nutrient channels in root membranes become less selective and less effective. This is where the concept of lockout becomes more than just a simplified explanation. It is not simply that nutrients are blocked from entering the plant. It is that the biochemical environment required for nutrient transport and utilization begins to break down. Cations and anions no longer interact in predictable ways. Transport systems become less efficient. Internal signaling becomes less stable. The plant is still surrounded by nutrients, but it can no longer properly organize them into usable biological functions. What makes this even more complex is that the plant does not experience this as a single failure. It experiences it as a gradual loss of efficiency across multiple systems at once. Growth slows not because energy is unavailable, but because the conversion of that energy into structure becomes chemically unstable. Nutrients may still be present in the solution, but the plant's ability to interpret and use them is reduced. At the same time, the plant continues making decisions based on incomplete information. It reallocates resources to compensate for perceived deficiencies. It adjusts root growth, modifies leaf development, and alters internal transport systems in an attempt to restore its balance. But if the underlying ionic and pH conditions remain unstable, these adjustments cannot fully resolve the problem. The system continues to compensate for an imbalance that persists at the chemical level. This is why plant responses to pH imbalance often appear complex or contradictory. What looks like multiple deficiencies is often a single systemic disruption affecting nutrient availability, enzyme function, and transport efficiency simultaneously. And this brings us back to the core idea of this entire system. Growth is not simply a matter of adding inputs. It is the result of a tightly regulated internal decision-making system that depends on energy production, nutrient balance, ionic stability, and environmental consistency, all functioning within a narrow range of compatibility. When these systems are aligned, the plant operates smoothly, energy flows efficiently, nutrients are absorbed and utilized correctly. Growth proceeds in a coordinated way across all structures. But when even one layer of this system becomes unstable, the plant must continuously adjust its internal priorities to compensate, often at the cost of overall efficiency. This is why growth is not a fixed outcome. It is a dynamic negotiation between chemistry, structure, and environment, unfolding moment by moment inside the plant. And once this becomes clear, the idea of plant growth changes completely. It is no longer about feeding or forcing expansion. It becomes about maintaining the chemical conditions that allow the system to function at all. And if those conditions drift too far, even slightly, the entire decision-making process inside the plant begins to reorganize itself around survival instead of growth. That is where stability stops being an advantage and becomes the foundation of everything that follows.